Hi, I'm Tess Corbett, and for the last year and a half, I've been working under Dr. Sengupta to explore the effects of the transition metal complex with HSA, or human serum albumin. And HSA is the most abundant protein present in the plasma of our body and has 4 partially selective metal binding sites with distinct preferences for different metal ions. These sites allow for the interaction of these metal ions with our protein without significantly changing the structure of our protein. The reason why we're so interested in this is because many people don't have clean drinking water due to metal contamination, and metal toxicity can lead to many different diseases and disorders such as cell death and even cancer. So this provides a basis of research for future treatments such as chelation therapy. For this series of experiments, we want to see if and at what concentrations these metal ions will change the structure of HSA. So to examine these interactions, we use CD spectroscopy and UV-Vis spectroscopy. And for our transition metal salts, we chose to use copper chloride and ferrous sulfate. To start off with our UV-Vis data, for our ferrous sulfate, we see that peak at 280 nanometers, which is just our tryptophan 214 absorbing light in that region. Additionally, we see a peak at 304 nanometers, which tells us that there's a new chromophore being developed in our solution. Chromophores can have a variety of different functions, and a great example I like to use is GFP, or green fluorescent protein. GFP is present in jellyfish, and it allows the jellyfish to fluoresce a bright green color. With our copper chloride UV-Vis spectra, again we see that peak at 280 nanometers, just again telling us that our metals ions are interacting with our protein in some type of way. HSA is a primarily alpha helical protein, so with CD spectra we tend to see a characteristic W shape. And with our ferrous sulfate, we see that characteristic W shape is retained under the 1 millimolar concentration. So we know that under 1 millimolar, ferrous sulfate is not significantly altering the structure of our protein. But whenever we look at our copper chloride spectra, we see that past that 200 micromolar point, that characteristic W shape is completely lost. So that tells us that that structure, the secondary structure specifically, has been significantly altered by our copper chloride. In the future, we would like to examine these interactions further using SDS page and HPLC, examine that new chromophore that I mentioned before at 304 nanometers with ferrous sulfate, and explore different transition metal salts such as silver or manganese. Thank you.